Hello and welcome back. Welcome to the second session of this SSC symposium titled Anomalies in Modern Astronomy Research. I am pleased to introduce Dr. Ignacio Trujillo, who will present Galaxies Lacking Dark Matter, Anomalies or a Natural Outcome of the Standard Model, where he will discuss some of the best known examples of dark matter deficient galaxies and what solutions the scientific community has proposed to explain the mysterious nature of these objects. Ignacio Trujillo is a researcher at the Instituto de Astrofísica de Canarias. He holds a PhD in astrophysics from the University of La Laguna and has been a researcher at the Max Planck Institute in Heidelberg and the University of Nottingham. Dr. Trujillo is a specialist in galaxy formation and evolution, and his current work focuses on ultra-deep imaging with the world's most advanced telescopes to test the dark matter paradigm and models of galaxy formation. Thank you for joining us, Dr. Trujillo. Muchas gracias. You can begin your presentation now.
Okay, thank you very much. I hope you can hear me well. And I also hope, despite Aviloev's work, that I'm a specialist, I have my mind open enough for discussing about these anomalies of the dark matter and galaxies. So the very first thing that I have to say is that I'm thanking Beatriz for inviting me, and also for the Society for hosting these very interesting events on talking about anomalies and what science can say about them. So I'm going to start talking about something that is currently a hot topic on extragalactic astrophysics, which is the claim that some galaxies apparently have no dark matter. But before going into the issue, I think it's better avoiding the term of dark matter to deal with this. And in fact, I'd like to start commenting on something different, which is the missing mass problem, which is, I think, the correct way of dealing with this anomaly. Because as soon as we say dark matter, we are, of course, giving a solution, implying that the problem that we are facing, which is a missing mass problem, is connected to an absence of a given substance, let's say something with matter, okay? So, but in fact, the problem is should be called the missing mass problem. And the problem is the following. So we are aware for more than 100 years now, so from the beginning of the 20th century, that the astronomical objects are in general moving much faster than what we should expect just by counting the mass that we see around and applying the Newtonian laws. That is something that we have been seeing for, as I said, more than 100 years ago. But it was 19 years ago when Fritz Zwicky, a Swiss astronomer, first put the name to the problem, and it called it the dark matter problem. And what Fritz Zwicky saw was that, or what he measured was that in the Coma cluster of galaxies, which is you can see here on the left, which is an association of nearly 1,000 galaxies moving at a high speed, nearly 1,000 kilometers a second. What he realized was that the galaxies were moving around each other way much faster than what he can predict just using the Newtonian laws, and therefore he said there should be something there that we are not seeing that is accounting for this extra velocity that these galaxies are moving. So that was the first, let's say, time that someone did some numbers and say there is something, or at least we don't understand well the gravity that is making the things to move very fast. No? In fact, the Fritz Zwicky calculation were that there should be some mass here on this cluster of galaxies that should be 400 times more mass, so it should contain 400 times more mass than what the one visually observed. But this observation was there for a long time, but there was not more data on this or relevant data, although there were some work on it. But then the situation became really popular on the 70s and the 80s, when the technology was good enough for starting to observe and to measure accurately, let's say, the movement of the material in the outer part of the galaxy. So this is a galaxy like our Milky Way, this like galaxy, full of stars. And as soon as you go farther and farther and farther away, instead of observing that the rotational velocity of the stars around the center of the galaxy is declining, as you should expect, what we see is that it's not even declining, but it is increasing or sometimes reaching a maximum value. This is a word that we can associate to pioneer work by Vera Rubin, Ken Ford, Albert Bosman. And so we can say that by the end of the 80s, it was very well recognized that there was a missing mass problems on the galaxy. It was not only on the general cluster of galaxies, but also on the galaxy itself. So, of course, this has been in the last 40 years the source of a strong debate about what could be the reason or the explanation for these anomalies. So why things in the universe are moving so fast compared to what we should expect by the matter that we see, the visible matter. There has been many alternatives, but I think that it's fair to group all these alternatives into groups. One is that thinking that, okay, so maybe our theory of gravity, that the one that we think is the correct one today, which is the general relativity by Einstein, is maybe not accurate enough, or it doesn't explain the movement of the objects when we try to explain it at the galactic scale or even extragalactic scale. But I will not go into that because it's a whole world. It's a branch of exploration, a branch of research, and I leave all these discussions, so this solution to the missing mass problem for the next talk by Professor Krupa, where he probably would be talking about all these alternatives to the general relativity. So what I would today concentrate more is on the second solution, which is the explanation that the missing mass it's because we are missing some matter, so this time a substance that we do not observe. There are many solutions. So this substance could be many different type of particles, and in fact, it could be that it's not only a single particle, but many different particles, so a complete different family of particles that are invisible, so that we can not see. And the reason why we do not see them by the light is because they do not interact, or if they do it very quickly with the electromagnetism. So therefore, they do not emit light, right? So we know matter with these properties. So, for example, neutrinos are dark matter, and we have measured that kind of matter. But however, neutrinos, although they are dark matter, so they have the properties of dark matter, so they are very quickly interacting with the normal matter. They move very fast to be the solution to the problem of the missing mass we have. So if the dark matter is a substance, it cannot be neutrinos. It has to be another type of matter. Is that a crazy idea? I would argue that it's not. So we have explored the matter in the universe up to a given range of energy in the Large Hadron Collider, but there are many order of magnitudes in energy and therefore in mass that we haven't got explored yet. So who knows whether there could be other substance with properties similar to neutrino, but moving more slow. So why dark matter and galaxies are so connected according to the standard, let's say, theory of dark matter and galaxies? And the main reason is the following. So when you look at the early universe, and this image on the top left is an image of the cosmic microwave background. So it's a picture, it's a photo of basically of the universe at the very beginning when it was a baby, let's say. the universe was extraordinarily homogeneous. So it's difficult to emphasize how extraordinarily homogeneous was the universe. But here, where in this picture, where we are actually observing the fluctuations, no, the the difference in temperature, it's only a tiny fraction. So it's only 1 part in 100,000. Okay, so this is extraordinarily homogeneous. So this is like um, as having 100,000 degrees, and only if you move along the entire universe, just make measuring fluctuation of only 1 degree. So it's extraordinarily homogeneous. Therefore, if you want to explain the current existence of galaxies within this paradigm, you need to have some extra dark matter that makes this tiny fluctuation to grow into the very structured and well-organized universe full of galaxies that we see today. So this extra gravitational pull, let's say, within the dark matter scenario is coming from this large amount of substance beyond the one that we can observe. So this is why the dark matter and the galaxies are so tightly connected in our understanding of the galaxies. So to have galaxies today, the galaxies that we see today should be filled by a halo of dark matter, because otherwise they should not even, we should not expect them to form, not even to evolve until the properties that we observe today. And however, we are aware, at least for the last 20 years, that there exist some galaxies that apparently the movements of the stars on those galaxies do not need dark matter. The one on the right is an example of this type of galaxies where the dark matter is not necessary. So you go, you measure the velocity of those stars, and the velocity of those stars is fully compatible with the number of stars we see. So we don't need an extra amount of invisible matter to explain the movement on these stars. Although these objects haven't been known for, let's say, nearly 20 years, nobody was worried about them. And the reason is because these galaxies were easily explained as a consequence of interactions with other larger systems around. So when you have collisions of galaxies or clouds of gas, sometimes you form this this collection of stars and gas that they are not still well settled gravitationally, so they are not in equilibrium, and therefore that is the reason why they have these elongated and distorted shapes. So astronomers were not worried about this system. In fact, they even put the name to those called tidal dwarf galaxies. And the reason is that we thought that, okay, this is just a phenomenon that is a transient phenomenon. So that with time that would be diluted on the space, and therefore this is not what anyone would call a stable system or something formed at the very beginning of the universe, and therefore this is not in contradiction to our standard paradigm of how the dark matter and the galaxies are connected. However, everything was changing, let's say just 4 years ago, when there was a shocking announcement of two apparently normal galaxies, like the ones that I'm showing here on the images, which seems to be dark matter deficient. So, in fact, the one on the left was the first one claimed by the group of Peter Van Dokkum in Yale, claiming that these objects have no dark matter, or if they has, it has to be so low that is basically so you cannot measure it. No, it's a very tiny amount. But if you look at these objects, they definitely look very different from the one that I showed you before, which was elongated, was clearly distorted. These objects look of a different nature because just by looking at this picture from the Hubble Space Telescope, you can see they look round, well organized. So it's not clear how you can have something apparently stable without dark matter. Okay. These two objects didn't came along. In fact, just a year later, the tension seemed to increase. The number of anomalies seemed to increase by a group of Chinese claiming that there were not only a couple of galaxies, but another 19 dwarf galaxies. Here you can see a couple of examples that apparently show also very low dark matter fractions. In fact, you just count the star, you just count the gas, and with that is more than enough to explain the velocities and the movements that you see. And even just a year ago, only a year ago, by the end of 2021, there was another example of a galaxy missing dark matter, or apparently lacking dark matter, this time with very high quality data, a very great good of experts and people. So the techniques were really very well developed, so a lot of tests. So, and another example of a galaxy claimed to have no dark matter. So, of course, this has been the source of an extraordinary debate on the extragalactic community, trying to explain whether this is something natural and a natural outcome of the dark matter paradigm, or whether we are facing with a really new anomaly and we should reject the dark matter paradigm because of this. Well, so the very first thing that put into discussion, so put into doubt the claim of some of these galaxies being anomalous, was that the very nature of these objects, which are extremely faint, these galaxies are so difficult to study because they are so faint that you really need the very large telescope, and so it's super difficult to measure a distance to these objects. Okay, but if you are wrong, and for whatever reason you measure a distance, or you assume a distance to this object that is much farther away than what it is in reality, then you overweight the amount of visible matter because you think the object is farther away when it should be. Therefore, you assume it has more stars to have the same brightness. And if you do that, you have less room for dark matter to explain the movement and the dynamics of these objects. So but for the very first object that it was claimed to have no dark matter, we did the work, and then we have good evidence to think that this object was closer than originally stated. So not only that, other work by other people have found that the first object that was claimed to have no dark matter, it's very likely rotating. And this is something that was not accounted before, where it was supposed the object to be just supported by random motions, let's say. But once you consider that the object is rotating, then you change the amount of mass that you have measured, and the amount of dark matter that you are measuring increases. Okay, so a combination of both problems with the distance and problems with your assumptions about the equilibrium of the object changes completely the amount of dark matter that you measure, okay, from nothing to have something much more in the line of what other galaxy has. So this object definitely is not still solved, and the debate is ongoing. However, for the other object that was claimed in 2019 in the Dragonfly 4, the velocity of the star was so low that no matter whether the object was closer in distance or the object was rotating or not, so the velocities of the star is so tiny that it has to be dark matter deficient. So there was no other possible explanation according to the previous lines. So but this time, what we did was to make a super deep images to try getting the visible, the distribution of the stars in the very outer part. And you can see here at the center what it was known from the Hubble Space Telescope, and you can see in the white and black background what we measure by going extraordinarily deep with our telescope. And you can see that there is a very, very diffuse but visible S shape around the galaxy, which is classical of objects when they are interacting with previous, with more massive systems. So if you remember what I was saying at the very beginning, the tidal dwarf galaxies with this elongated and distorted shape. So here you have a reproduction. And we can even see that this tail of a star, of extremely dilute stars, are pointing to a nearby massive neighbor, which we think is the reason of this tidal distortion of the galaxy. So if you can observe now that the stars are getting apart from the galaxy, that is the same phenomenon that it could have just a little bit of time before removed the halo of dark matter around these objects. So in that sense, we think that the reason why this galaxy is not having dark matter is probably because that dark matter was disrupted, it was removed from this object in the past because of the interaction with this neighbor. And finally, what about the other 19 galaxies that were claimed by the Chinese group? So in that case, the explanation within the natural, within the, let's say, the standard dark matter paradigm has been that the true distribution of stars in these objects has not been considered. This is a very interesting case where someone found an alternative explanation just in a few days. So the Chinese group put the result on the public repository, so everybody can see it. And just a few days, it came a natural explanation of what could just been happening and for explaining what was going on. In this case, this is an example of a dwarf galaxy. And remember that when we make pictures of galaxies, what we see is a projection of a structure that in reality is a three-dimensional structure, okay? So we see only a face of the multiple shapes that the object can have. So on the work conducted by the Chinese group, they assume to explain the dynamical properties that the objects are just disks of galaxies that we see with different orientations. But however, we know that this type of very small galaxies, in reality, they are not thin objects, but much thicker stuff. But just using this information that we know from other objects, we could explain all these dark matter deficient, these 19 objects, without any problems. So this work was put into question very quickly. So let me finish just commenting on the lines that our group is doing to try getting more information about these galaxies without dark matter, okay? And what we are doing as a group is to use extraordinarily deep imaging, as the ones that I showed you before with showing the tidal tails of the galaxies. And what we do is using the today's larger telescopes that includes telescopes in Hawaii, like the Gemini, the LBT in Arizona, or the GTC in the Canary Islands. So these are telescopes which have a mirror diameter of the order of 8 to 10 meters, and therefore they can take extraordinarily faint, they can detect extraordinarily faint features on the astronomical images. In fact, this telescope, when you know how to take pictures and deal with the right treatment of the data, you can observe and you can detect brightness that are 1,000 times fainter than the brightness of the darkest sky that you can have on Earth. So if any one of you have been lucky enough to go to a professional observatory, an astronomical professional observatory, you know that when you are there and there's no moon on the sky, the darkness is so impressive that you can barely see your hands, right? So these images, the new technology is capable of observing up to 1,000 times fainter than these darker conditions. Therefore, if you have such an ability to explore the very faint features around the galaxy, you can detect whether they are being destroyed or not, and therefore understand better whether the claims of having or not dark matter are really explainable in terms of interaction with other systems or not. So this is an example just to show you how the technology has improved in the last 20 years. So this is an image of the first galaxy lacking dark matter that we were discussing before. And you can see how in only 20 years, from basically seeing nothing on the sky, we now can see very beautiful images of those galaxies. And therefore, we are capable of exploring the outskirts of these objects in amazing detail. In fact, that only in 20 years, we have made a giant step forward of increasing our capabilities of detection of any structure by a factor of nearly 100. So to finish, I think these are my takeaway messages. So we have been discovering an increasing number of dark matter deficient galaxies in recent years. Some of these no dark matter galaxies could be explained relatively easy because they have been an incorrect interpretation of the data, like distances, orientations, structural properties of the objects. Other galaxies without dark matter can be interpreted by the loss of that component, of that matter component, because they are interacting with other objects. And therefore, I think that it's fair today. I don't know tomorrow, but today I think it's fair. It's fair claiming that we have no firm dark matter. We don't have a firm candidate galaxy without dark matter that cannot be explained within the standard dark matter paradigm. And that's all. Thank you very much for attention. I'm very open. I'm happy to answer questions that you could have.
Hello, and thanks, Dr. Trujillo. That was a very interesting and insightful presentation. Dr. Trujillo, what do you envision the James Webb Telescope will tell us about dark matter and dark matter lacking galaxies?
Well, it's a wonderful technology. It allows us to explore extraordinarily faint objects, because it's a very large telescope, much larger than the Hubble, and it's also working at the near infrared that help us to catch, let's say, fainter stars. And therefore, it will allow us in this field to make much accurate dynamic estimations of the movement of stars in other galaxies. And also, it will allow us to study galaxies even farther away. And also, I was here only dealing with the connections between dark matter and galaxies. But of course, the problem of dark matter is explored at much larger scale, like galaxy clusters, where we can also explore other interesting phenomena like the intracluster light that I have not got the time today to discuss. So yes, so I expect a large number of interesting things from the James Webb Telescope in the next few years in this field.
Muchas gracias. Thank you very much for the answer. So we have a speaker, Dr. Pablo Krupka, in wanting to ask you a question directly, so I'll put him on stage.
Sure.
Okay, Dr. Krupka, you're on stage.
Hello, can you hear me?
Yes,
yeah, we can.
Okay, hi, thank you. Thanks, Ignacio, for this very nice presentation. I really I liked the historical overview, and I think I go along with you with a shorter distance. I think the 13 megaparsec seems to be the more realistic distance. But just one word of caution. It's not so easy to strip a galaxy of its dark matter, and I know I've seen with some alarm that this is now being put forward in the literature. But if one actually does calculations, it doesn't work. Especially, one needs a really strong encounter to remove the outer parts, and repeated encounters, and it becomes it's basically not possible really because you're always left with dark matter within the system as well. You see, so even though one strips the outer parts, if that were even possible, then you are still left with the dark matter within the observed body, and so not that much is gained. So just a word of
I
caution.
agree, Pavel. Thanks for your remark. But definitely, if we see that the galaxy is being destroyed, let's say, or getting apart, we definitely would need to consider the assumption that the object is in equilibrium, I would say, and therefore the claims that the use of the regular equilibrium equations that people are normally using for infer that there is a dark matter needs to be put into a question. So I could agree with you that maybe it's not such easy just to remove dark matter, but definitely then. I don't know how to interpret the measurements of the dynamics of the object when I clearly see that it's interacting with another more massive galaxy, right?
Well, it's interacting. Yes, usually interaction enhances this velocity dispersion, right? So that actually sort of goes the other direction. It's. I mean, these systems are a real problem for the dark matter framework. They really are. I mean, it's. But I share the distance with the closer distance. But it actually shifts the whole problem towards a different gravitational theory, which then easily resolves all these problems. And I'm not saying that because I hate dark matter. I mean, I'll be giving my talk in a moment, but that's just the evidence we have. I know you're not mentioning Mond at all, but
I left up to you, of course. I don't want to spoil your presentation. I just said, and in fact, I think I was fair enough to say that there's like two branches of explanation for the missing mass problem. So I know, but my side was to try to present the dark matter paradigm. And leave for you to the alternative explanation, let's say.
Yeah, thanks. And thanks for the presentation. It was very nice.
Yeah. Thank you very much, Dr. Krupa. We'll remove you from stage. And so we have one question from Robert Schutz, which I will put on stage. He's asking, if you used Einstein's equation instead of Newton's equations, would you get the same result for dark matter to explain galaxy formation?
Yes. So for this regime, let's say whether we are not the stars are not moving fast or close to the velocity of the light, and also the gravitational strength is not as important. Okay, so we are not in the, let's say, general relativity regime. So we do not have strong gravitational fields nor high velocity movements, and therefore the general relativity equation just transforms gently into Newtonian's approximation, let's say, Newtonian's equations, and therefore the use of Newtonian equations here is perfectly valid in terms that the regime where we are applying is consistent with not being relativistic. So the answer, the short answer is no matter that you use general relativity. You complicate your life using general relativity, but you don't need it.
Fair enough. Thank you very much for the insightful answer.
Okay.
I don't see we have any additional questions right now. So would you want to share some final thoughts about your presentation or the scope, or more like where are you going with your research or with this line of investigation? Something that you want to share before we close?
No, I just would like to keep insisting that this is an open debate, and that we are doing our best to go forward and try to see whether these anomalies that we see, corresponds to new fixes or not. So I do not completely share what it was stated before, that the the research community in general is against anomalies. I think, on the contrary, we are, or at least myself and my group, so we are really open to study them, because in anomalies, they are, a very there could be powerful lines of research to detect new things, right? So
I agree with you. It's basically the foundation of science.
Exactly.
Or it should be. That's the point. It should be.
Of course, there would be people extremely conservative on the research community, but I would say also that there's a lot of people very much interested on exploring the non-obvious phenomenon, because so this is the reason why we are so much interested in science. So I would just, my question would be, do not push much, evil scientists or so. On the contrary, I think most of the community are extremely happy and open to explore the unexpected, let's say.
Yeah, I would agree with you with the inquiries and the curiosity-driven mind should be the fit of every scientist. And I would like to maybe invite all the attendees and the people that are hearing this recording maybe in the future, and other scientists to join the Society for Scientific Exploration, which we use as an international forum to explore these type of questions and many others. So thank you very much, Dr. Trujillo. That was a very exciting and insightful presentation. So we will close the session now and have a few minutes before our next presentation. So please make use of the social lounge. Thank you all for coming, and gracias nuevamente usted, Dr. Trujillo, for this presentation on this very interesting topic.
Thanks to you all.